Well, I am phased.
By what?
The phases of nuclear matter.
So, what's phasing you about it?
Well, I get that there's liquid water, and if you heat it up, it becomes gaseous steam. And if you take away heat, it becomes solid ice. But what I don't understand is phase diagrams and all this pressure.
Well, like you said, as you heat it up, or add energy, so to say, you raise the temperature. Once you reach a certain point, however, adding more energy does not increase the temperature of the water. For instance, once you reach the boiling point at 100 degrees Celsius, it stays at 100 degrees Celsius until you overcome the latent heat of vaporization. As long as there is still liquid, the gas and liquid phases are in coexistence. Once all of the water turns to gas, the temperature can then continue to rise. Transitions such as this, which involve a latent heat and phase coexistence, are called first-order transitions. Now, to your phase diagram. It shows how pressure affects the phase transitions of water. As the pressure goes up, the boiling point of water goes up. At a pressure of about 200 times the atmospheric pressure, and a temperature of 374 degrees Celsius, a critical point is reached. There, phase transitions are continuous and are called second order.
So transitions where two phases coexist are first order, and transitions without this coexistence are second order. But why does increasing pressure increase the temperature at these locations? And how does this have to do with nuclear science?
Well, just like a group of atoms or molecules depends on temperature and pressure, so too does the state of a nucleus depend on temperature and density of nucleons.
In their lowest energy states, nuclei behave similar to liquids. They can be heated up significantly through collisions with other nuclei. As more energy is added, the nuclear liquid evaporates. Just like water, there should be a phase coexistence and a latent heat of vaporization. There should also be a critical point for nuclear matter where there is no coexistence between the two phases. Currently, experiments are looking to find the temperature and density where the critical point of nuclear matter is, and to verify if these theoretical expectations are correct. Transition between nuclear liquid and a gas of nucleons is not the only phase transition being looked at. At higher temperatures and densities, the nucleons also go through a transition. Each nucleon contains its own quarks and gluons. These quarks and gluons are confined to their nucleons, so we can't detect them individually. However, if they were an extremely dense gas of hadrons, then the quarks and gluons might be free to travel across the whole nuclear volume. This is called the quark-gluon plasma. If you remember our discussion on the expansion of the universe, you'll recall the early universe was dominated by quarks and gluons. By studying this phase of nuclear matter, we can get an insight into the state of the early universe. Also, studying phases of nuclear matter will allow us to understand neutron stars. After a star with sufficient mass undergoes a supernova explosion, its iron core remains. Gravity is so strong in the situation that it overcomes the repulsive force of the nuclei. At this point, nucleons separate from the nucleus, and the protons undergo a reversal of beta decay, becoming neutrons. This makes a dense ball of neutrons a neutron star. Major research institutions are studying the phases of nuclear matter and looking for a deeper insight into the universe.
Huh, that's pretty neat stuff. Maybe this isn't so phasing after all.
Well, I'm glad to hear it, man.
In fact, I think I've transitioned into a new phase of understanding.
Well, that's even better. And hey, if you need any more help, I'll see you next week.